Close your eyes. Take one slow breath in and let it go. Right now, as you lie here, there are two objects moving through interstellar space. Not in a film, not in a simulation, right now, tonight, in the real universe, in the actual dark between actual stars. They are small, smaller than a car, smaller than most things you own. Each one weighing less than a grand piano, each one carrying a golden disc etched with the sounds and images of a world that launched them almost 50 years ago and has not stopped thinking about them since. They are called Voyager 1 and Voyager 2, and they are the furthest things humanity has ever made. Voyager 1 is, as of this moment, more than 24 billion kilometers from the Sun, a number so large that it takes light, the fastest thing in the universe, more than 22 hours to make the journey from Earth to the probe. A round-trip message takes nearly 2 days, and in the time it takes you to read this sentence, it has moved another 17 kilometers deeper into the unknown. It is still sending data. It is still alive. After nearly 5 decades in space, launched by a civilization that hadn't yet invented the personal computer, Voyager 1 continues to transmit signals home at the power of a refrigerator light. Those signals travel for 22 hours at the speed of light before reaching our antennas. And when they arrive, they carry real measurements, real science, real information from the edge of everything we've ever reached. Tonight, we're going to follow them. From the launch pad in Florida in the summer of 1977, through the inner solar system and the asteroid belt, past Jupiter with its violent, beautiful storms, past Saturn and its impossible rings, into the outer dark beyond Neptune, through the heliopause, the boundary where the sun's influence ends and true interstellar space begins, and into the silence beyond. This is the story of Voyager, the greatest journey in human history, told slowly, told softly, for the hours when the day is over and the mind is ready to rest. There is nowhere you need to be, nothing you need to do. Just breathe and listen. We begin at the beginning. In the late 1960s, a young aerospace engineer named Gary Flandreau made a discovery that would change the history of human exploration. Working at the Jet Propulsion Laboratory in Pasadena, California, Flandreau was tasked with identifying possible trajectories for future outer planet missions. He was looking for efficient routes, ways to get a spacecraft to the outer planets without the journey taking decades. The outer solar system is vast. Jupiter is 5 times farther from the Sun than Earth. Saturn is nearly 10 times. Uranus is 20. Neptune, 30. With conventional propulsion, a mission to Neptune would take 30 years or more. What Flandreau discovered was a rare alignment. Once every 175 years, the outer planets, Jupiter, Saturn, Uranus, and Neptune, arrange themselves in a curved arc on the same side of the solar system. When this happens, a spacecraft can be launched on a trajectory that uses the gravitational field of each planet in turn as a slingshot, picking up speed and redirecting toward the next target without any additional propellant. The physics behind this, called a gravity assist or gravitational slingshot, is elegant. When a spacecraft approaches a planet, it falls into the planet's gravitational field and accelerates. If the trajectory is calculated correctly, the spacecraft can swing around the planet, picking up some of the planet's orbital momentum, and emerge on the other side, moving significantly faster and in a new direction. No fuel burned, energy effectively stolen from the spinning solar system itself. The alignment Flandreau identified would begin in the late 1970s. The window was narrow. To take advantage of it, a mission would need to launch by late 1977. The decision was made. The mission was approved. The probes were built. They were named Voyager. Let your shoulders drop. Feel the surface beneath you, holding you completely. There is a particular quality to the way history turns on small moments. A calculation made by a 20-something engineer at a desk in California. A window that opens once every 175 years. The decision to build 2 spacecraft and send them through that window before it closed. The next time that alignment occurs, no human alive today will be alive to see it. We caught it. By the narrowest of margins, we caught it. And we sent them out. Both Voyagers were built at the Jet Propulsion Laboratory over several years of intense development. They were designed to survive the radiation belts of Jupiter, the frigid temperatures of the outer solar system, the vacuum of space, and the constant bombardment of micrometeorites and cosmic rays. They were built with redundant systems, backup computers, backup radios, backup power circuits, because out there, if something broke, no repair crew would ever arrive. They were built, in other words, to last, to keep going, to keep transmitting long past any reasonable expectation of their survival. They exceeded every expectation ever held for them, and they are still out there. Voyager 2 launched first. On the 20th of August, 1977, it lifted off from Cape Canaveral, Florida, atop a Titan Centaur rocket. The sky was clear. The launch was perfect. Within minutes, the spacecraft was in orbit, and within hours, it was on its trajectory toward Jupiter. 16 days later, on the 5th of September, Voyager 1 followed. Despite launching second, it was placed on a faster, more direct trajectory that would overtake its twin and reach Jupiter first. The naming reflects launch order, not travel order. A small confusion that has puzzled people for decades. Both spacecraft were roughly the size of a small car. Each weighed about 825 kilograms at launch, including propellant. Each carried 11 scientific instruments, cameras to photograph the planets and their moons, magnetometers to measure magnetic fields, instruments to detect charged particles and plasma waves, ultraviolet and infrared spectrometers to analyze the chemical composition of atmospheres and surfaces, and each carried a golden record. The Voyager golden records were the idea of Carl Sagan, the astronomer and writer who had a gift for thinking about what it means to be human in a universe of unimaginable scale. Sagan chaired the committee that assembled the record's contents, working with a small team to select sounds and images that might communicate something meaningful about Earth and its inhabitants to any intelligence that ever found the spacecraft. The records contain 116 images, scientific diagrams, pictures of landscapes and cities and animals and people, mathematical and physical information that any technologically advanced civilization could presumably decode. They contain greetings in 55 human languages, from Akkadian, one of the oldest written languages, to Wu Chinese. They contain sounds, rain, wind, surf, thunder, the songs of birds, the sounds of whales, the cry of a newborn, the sound of a kiss, footsteps, laughter. And they contain music. 90 minutes of music from across human history and across human cultures. Bach, Beethoven, Mozart, Louis Armstrong playing melancholy blues, Chuck Berry's Johnny Be Good, a Navajo night chant, Pygmy Girls' initiation song, Peruvian wedding song, Georgian chorus, Japanese shakuhachi, Azerbaijani bagpipes. The cover of each record is electroplated with a thin layer of uranium-238, which decays at a known rate and could tell any finder how long the record has been traveling. The records were not primarily intended to be found. The probability of any intelligent civilization ever encountering these tiny spacecraft in the incomprehensible vastness of interstellar space is vanishingly small. They were, more than anything, a statement. A message sent not to the cosmos but to ourselves, about who we are and what we value and what we thought worth sending into the dark. Carl Sagan described the golden record as a bottle thrown into the cosmic ocean. Let that image rest with you for a moment. A bottle in the cosmic ocean, each one 24 billion kilometers away right now, carrying the sound of rain and laughter and Bach, drifting through a silence so complete that sound itself does not exist. Breathe in slowly. Let the image settle, and continue. On the 5th of March, 1979, Voyager 1 made its closest approach to Jupiter. Nothing anyone had seen before could have fully prepared them for what the cameras sent back. Jupiter is enormous. Not large, enormous. Its diameter is 11 times that of Earth. More than 1,300 Earths could fit inside it. It is so massive that it contains more than twice the mass of all other planets in the solar system combined. If you took every other planet and every moon and every asteroid and every comet and every fragment of rock and ice in the solar system and added them all together, Jupiter would still outweigh that sum. And it is not quiet. The cloud bands that stripe Jupiter's visible surface are not gentle wisps. They are continent-wide rivers of ammonia ice and hydrogen sulfide, moving in opposite directions at velocities that would make Earth's most powerful hurricanes look like a light breeze. The boundary zones between these rivers are sites of constant, violent turbulence, spiraling eddies and vortices that form and dissolve over days and weeks. And then there is the Great Red Spot. The Great Red Spot is a storm, a single, continuous storm that has been raging in Jupiter's southern hemisphere for at least 350 years. The entire length of time humans have had telescopes powerful enough to see it. At the time of the Voyager flybys, it was approximately 3 times the diameter of Earth. Its winds moved at over 400 kilometers per hour. Its color, that deep, burnt orange-red, comes from complex organic molecules formed by the action of ultraviolet light on the ammonia and phosphine gases in Jupiter's upper atmosphere. Europa was smooth, eerily, almost perfectly smooth. Its surface was crisscrossed with a network of lines, fractures in a layer of water ice that covered the entire moon. The ice was relatively thin, geologically speaking, and beneath it, the gravitational tidal heating that made Io volcanic appeared to be keeping something liquid. Beneath Europa's ice, the model suggested, there was an ocean of liquid water. Liquid water. In the outer solar system, around a moon orbiting a gas giant that never came close to being warm enough for water to exist on its surface. The implications were immediate and profound. Liquid water is, as far as we know, a prerequisite for life as we understand it. If liquid water exists beneath the ice of Europa, an ocean that may be larger than all of Earth's oceans combined, then the possibility of life in that ocean cannot be dismissed. We have not yet sent a mission to that ocean. We are working on it. Europa waits. Let your breathing slow even more now. In through the nose, out through the mouth. You are warm and still, held by gravity, on a world that is extraordinary in its own right, and yet one of hundreds, perhaps thousands of worlds in our solar system alone that may hold secrets we have barely begun to explore. The story continues. Saturn has rings. We have known this since Galileo first observed the planet in 1610 and wrote, puzzled, that it appeared to have ears. What he was seeing, though his telescope was too crude to resolve it clearly, were the rings. Christian Huygens in 1655 correctly identified them as a flat disk surrounding the planet. Later observations revealed that the disk was divided into separate rings, each one a different distance from the planet, each one apparently composed of countless small particles. We knew all of this before Voyager. What we did not know was what the rings actually were. Not in detail. not in the extraordinary, overwhelming detail that the Voyager cameras revealed when the spacecraft finally arrived at Saturn. Voyager 1 reached Saturn on the 12th of November, 1980. Voyager 2 followed 9 months later, in August 1981. What they showed us was one of the most beautiful and baffling structures in the solar system. The rings of Saturn are not a few simple bands. They are a vast, complex, dynamic system spanning nearly 300,000 kilometers from the planet's equator. From a distance, they appear to be smooth and continuous. Up close, from the perspective of a spacecraft threading through the ring plane, they resolve into thousands of individual ringlets, each one a separate, narrow band of material with gaps of varying width between them. The particles that make up the rings range in size from tiny grains of dust to house-sized boulders. Most are made of water ice, some of the purest water ice in the solar system, reflecting sunlight so efficiently that the rings shine with a brightness that seems almost artificial. Interspersed with the ice particles are darker, dusty materials that create the subtle color variations visible in Voyager's images. The origin of the rings remains a subject of debate. They may be the remnants of a moon that strayed too close to Saturn and was torn apart by tidal forces. They may be material left over from the formation of the Saturn system that never coalesced into a moon. The rings are, in geological terms, young, perhaps only a few 100 million years old, which raises the unsettling possibility that there was a time not long ago in cosmic terms when Saturn had no rings. And there may be a future equally distant when the rings have been absorbed into the planet and are gone. We are, by this reckoning, extraordinarily lucky to exist at a moment when the rings are there to see. But it was Saturn's largest moon, Titan, that produced perhaps the most profound surprise of the Saturn encounter. Titan is the only moon in the solar system with a substantial atmosphere. Not a thin, wispy atmosphere like that of Mars, but a thick, opaque haze of nitrogen and organic compounds so dense that it completely hides the surface. Voyager's cameras could not see through it. What the spectrometers detected, however, was extraordinary. The atmosphere of Titan contained complex organic chemistry, hydrocarbons, nitriles, and other carbon-based molecules that had never been found in the atmosphere of another world. The chemistry of Titan's atmosphere appeared to resemble, in some ways, the chemistry of Earth's early atmosphere, before photosynthesis began producing oxygen, before the first living cells began to metabolize. Titan could not harbor life as we know it. Its surface temperature is around -179 degrees Celsius. At that temperature, water is frozen as hard as granite. But on Titan, as later missions would confirm, methane plays the role that water plays on Earth. There are methane lakes and methane rivers and methane rain, cycling through a methane weather system that is eerily familiar in its form and utterly alien in its substance. And beneath the surface, models suggest there may be a subsurface ocean of liquid water mixed with ammonia. Saturn, it turned out, was not just a jewel to look at. It was a system of worlds, each one different, each one strange, each one capable of spending an entire mission just trying to understand. Settle deeper into the dark around you. Feel how quiet the room is, how still the air. Somewhere, at this moment, light that left Saturn 30 minutes ago is reaching Earth. The planet is still there. The rings are still turning. The storms are still moving. Titan's methane rain is still falling. All of it continues, whether we are watching or not. And the Voyagers flew through it and looked and sent us pictures and kept going. After Saturn, the missions diverged. Voyager 1's trajectory, optimized for close flyby of Titan, had bent it out of the plane of the solar system. It was heading upward, northward relative to the plane in which the planets orbit, and would encounter no more planets. Its job was done in terms of planetary science. It would continue into the outer solar system and beyond. Voyager 2, on the other hand, had been kept on the Grand Tour trajectory. It still had 2 planets to visit. On the 24th of January, 1986, Voyager 2 became the first, and to this day only, spacecraft to visit Uranus. Uranus is strange. Most planets spin on an axis that is roughly perpendicular to the plane of their orbit. Earth's axis is tilted about 23 degrees. Mars is similar. Jupiter is barely tilted at all. But Uranus is tilted 98 degrees. Essentially, it orbits the Sun on its side. Its poles point toward the Sun at solstice, meaning one pole receives sunlight continuously for 42 years, then the other does for another 42 years, while the first is in continuous night. The cause of this extreme tilt is thought to be a massive collision early in the solar system's history, a planet-sized body striking Uranus at an angle that knocked it over. The collision may also explain why Uranus radiates almost no internal heat, unlike the other giant planets. Whatever heat the planet once generated internally may have been disrupted or lost in the impact. Voyager 2 found a world shrouded in blue-green methane haze, nearly featureless in visible light. Its instruments detected a magnetic field tilted at a remarkable 59 degrees from the planet's rotational axis and offset from the planet's center, suggesting a complex internal structure unlike any other planet we had studied. 10 previously unknown moons were discovered. 2 new rings were found. And then the encounter window closed and the spacecraft moved on. 4.5 years later, on the 25th of August, 1989, Voyager 2 made its final planetary encounter, Neptune. Neptune had been something of a mystery even before Voyager. It was the last planet discovered by mathematical prediction rather than observation. Its existence was inferred from perturbations in Uranus's orbit, and it was found almost exactly where the calculations predicted. But we knew almost nothing about its surface or atmosphere or moons. What Voyager 2 found was a world of extraordinary dynamism. Neptune, despite being the most distant planet and receiving only a tiny fraction of the sunlight that Earth receives, has the strongest winds in the solar system. At the time of the Voyager flyby, wind speeds of over 2,000 kilometers per hour were measured. A storm system called the Great Dark Spot, structurally similar to Jupiter's Great Red Spot, dominated the southern hemisphere, a swirling vortex the size of Earth. And there was Triton. Triton is Neptune's largest moon, and it is one of the strangest objects in the solar system. It orbits Neptune backwards, in the opposite direction to Neptune's rotation, which is almost certainly not original. Objects that form around a planet orbit in the same direction as the planet's spin. An object orbiting backwards was captured from somewhere else. Triton is almost certainly a Kuiper Belt object, a body from the outer reaches of the solar system that was captured by Neptune's gravity billions of years ago. The capture would have been catastrophic for Triton. The gravitational stresses of being captured into orbit would have melted the entire interior, resetting whatever geological history it had accumulated in the Kuiper Belt. But what Voyager saw on its surface was not a frozen dead world. There were geysers, active nitrogen geysers, erupting from the surface and rising kilometers into the thin atmosphere. The sunlight, faint as it is at Neptune's distance, was warming dark patches of subsurface material, creating pressure beneath the surface ice that erupted in dark plumes when it found a weak point. A moon captured from the outer darkness with active geysers, at the edge of the solar system, in 1989. It was the last planetary discovery of the Voyager mission. After Triton, there were no more planets, just the long dark, just the slowly fading warmth of a star 4.5 billion kilometers away, just the void, and the 2 small spacecraft, still moving, still transmitting, still alive. On the 14th of February 1990, at the request of Carl Sagan, the cameras of Voyager 1 were turned around. By this point, the spacecraft was approximately 6 billion kilometers from the Sun, already in the outer solar system, already far beyond the orbit of Neptune, already further from Earth than any human-made object had ever been. The cameras were not designed to look back. The Sun was close enough, in angular terms, to risk damaging the imaging system. The scientific case for turning around was weak. What useful data could be gathered by photographing the solar system from the outside? But Sagan had been arguing for this image for years. He understood that the value was not scientific, but humanistic. That seeing the Earth from that distance, a tiny, insignificant point of light in the immensity of space, would do something to us that no amount of words or equations could accomplish. The photographs were taken, 60 frames covering most of the solar system, and there, in one of the frames, was Earth. A pale blue dot, a single pixel, fractionally colored by the scattering of sunlight in the camera's optics, suspended in a beam of scattered light in the darkness of space. Carl Sagan wrote about this image in words that have not aged and will not age. He wrote that from this distant vantage point, Earth might not seem of any particular interest, that there are no hints in it of who we are or what we have done or what we have believed about ourselves and our place in the universe, that our planet is a lonely speck in the great enveloping cosmic dark, that in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves, that the Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment, the Earth is where we make our stand. He wrote that to him, the pale blue dot underscored our responsibility to deal more kindly with one another and to preserve and cherish the only home we have ever known. This image, taken by a spacecraft launched with 1970s technology at the request of a man who died in 1996, from a camera that has since been switched off to conserve power, remains one of the most profound photographs ever taken. Not because of what it shows, because of what it doesn't show. It doesn't show the borders, the wars, the hierarchies and the arguments and the certainties that divide us. It doesn't show any of the things we spend so much time and energy fighting about. It shows a dot, a pale blue dot in an ocean of black, and somehow that is enough. Rest your eyes now. Feel how comfortable you are. The world outside is continuing. It will continue. The morning will come and you will be there for it. But right now, in this moment, all of that is very far away. Here, there is only the dark and the warmth and the quiet. And somewhere out there, still moving, the spacecraft that took that photograph continues on. There is a room at the Jet Propulsion Laboratory in Pasadena, California, called the Deep Space Network Operations Center. It is not a glamorous room. It has the functional, slightly tired look of any control room that has been in continuous operation for decades. Banks of monitors, wheeled chairs, overhead lighting that is bright enough to work by, but not warm enough to be comfortable. The hum of air conditioning keeping the electronics cool. From this room, and from 3 antenna complexes spread around the globe, in California's Mojave Desert, near Madrid in Spain, and outside Canberra in Australia, human beings maintain contact with every active spacecraft in deep space. Mars rovers and orbiters, solar observation missions, the New Horizons spacecraft, which flew past Pluto in 2015, and Voyager 1 and Voyager 2. The 3 antenna sites are positioned roughly 120 degrees apart in longitude, which means that as the Earth rotates, at least one of them is always facing any given point in deep space. The contact with Voyager is not continuous. The antennas must be shared among multiple missions, but it is regular. Every day, somewhere on Earth, a large dish antenna swings to point at a piece of empty sky and listens. The signal it receives is extraordinary in its fragility. By the time Voyager's transmissions reach Earth, they have spread across more than 22 light-hours of space. The power of the signal, which leaves the spacecraft at 23 watts, about the power of a dim light bulb, has been diluted across a sphere billions of kilometers across. What arrives at the antenna is a whisper of energy so faint that it would take 20 billion years to accumulate enough of it to power a single smartphone for 1 second. And yet, the antenna hears it, amplifies it, converts it from radio waves into digital data, and sends it to the operations center, where it is decoded and distributed to the scientists and engineers who have been waiting, sometimes for 22 hours, to see what the spacecraft has to say. The people who do this work are not famous. Their names are not known outside their field. But they are the ones who maintain the connection, who keep the thread alive between a civilization and the furthest things it has ever made. There is something quietly heroic in that, something worth holding gently as you settle towards sleep. Somewhere right now, a large dish is turning toward a point in the sky. A signal is arriving. Someone is listening. Breathe in that thought and let it carry you. For decades, scientists spoke of the heliopause as a theoretical boundary. The heliosphere, the bubble of space dominated by the sun's magnetic field and the constant outflow of charged particles known as the solar wind, was known to extend far beyond the planets. The solar wind blows outward in all directions from the sun at speeds of 400 to 800 kilometers per second, carrying with it the sun's magnetic field, filling the inner and outer solar system with a thin, hot plasma. At some distance from the sun, the models predicted, the solar wind would weaken. The pressure of the interstellar medium, the thin gas and magnetic field that fills the galaxy between star systems, would push back. The solar wind would slow, compress, and eventually stop. The point where this happened, where the sun's domain ended and true interstellar space began, was called the heliopause. Nobody had ever been there, until Voyager. Voyager 1 crossed the termination shock, the first boundary where the solar wind slows dramatically, in 2004, at a distance of approximately 94 astronomical units from the sun. It spent the following years in the heliosheath, the turbulent outer region of the heliosphere where the solar wind is compressed and heated before finally meeting the interstellar medium. On the 25th of August, 2012, the plasma wave instruments aboard Voyager 1 detected a sudden change. The density of charged particles increased sharply. The magnetic field direction shifted. The energetic particles from the solar wind dropped abruptly. The galactic cosmic rays, high-energy particles from outside the solar system, which had been partly blocked by the heliosphere, increased dramatically. It had crossed. Voyager 1 was in interstellar space. The announcement, made in September 2013 after careful analysis of the data, was historic. For the first time in human history, something we had built had left the solar system, had crossed from the sun's domain into the space between stars, was, by any meaningful definition, in a different part of the galaxy from the one it had started in. The data it sent back was not what scientists had expected. The magnetic field direction was different from the models. The density of the plasma was higher. The structure of the boundary itself was more complex, more irregular than theory had suggested. The heliosphere, it turned out, was not spherical, as most models assumed, but elongated, pushed inward on the side facing the direction of the sun's travel through the galaxy, extended on the opposite side. The models had been wrong. The universe had corrected them. That is how science works. You build a model. You send something to test it. The universe tells you where the model was wrong, and you build a better model. Voyager 2 crossed the heliopause on the 5th of November 2018 at a distance of approximately 119 astronomical units from the Sun, a different location than Voyager 1's crossing, giving scientists 2 data points on the shape and properties of this boundary for the first time. The data from the 2 crossings together began to paint a picture of the heliosphere's true shape. And the picture was stranger and more complex than anyone had anticipated. The boundary wasn't where the models predicted. The shape was completely wrong. The interstellar medium had unexpected properties. Every answer generated new questions. That is the nature of exploration. Breathe in, out. In, out. Your body is heavy. Your mind is soft. The questions can wait. They will always be there. The universe is not going anywhere. Let the weight of the day dissolve. Let the thoughts float past without catching them. The story is almost done, but not quite. Part 8. Still transmitting. The Voyager probes are powered by radioisotope thermoelectric generators, RTGs. These devices work by converting the heat produced by the radioactive decay of plutonium-238 into electricity. They have no moving parts. They do not require sunlight. They do not need to be pointed in any direction or refueled. They simply generate heat, which generates electricity, steadily, reliably, as the plutonium decays. When Voyager 1 and 2 were launched, each RTG was generating approximately 470 watts of electrical power, the same amount of power used by a small space heater. Nearly 5 decades later, the decay of the plutonium has reduced this output. Each spacecraft now generates roughly 250 to 300 watts. That is enough. That is enough to keep the spacecraft's computers running, enough to power the science instruments, those that have not been switched off to conserve power, enough to power the transmitters that send signals back to Earth across more than 22 light hours of empty space. But it is not unlimited. Over the years, mission managers at the Jet Propulsion Laboratory have made a series of difficult decisions about which systems to keep running and which to shut down. Heaters have been turned off, allowing parts of the spacecraft to drop to temperatures that would destroy most electronics, but which the Voyager instruments, built with extraordinary robustness, have survived. Scientific instruments have been powered down one by one as the power budget tightened. In 2023, engineers discovered an anomaly in Voyager 1's flight data system, the computer that packages the scientific and engineering data for transmission to Earth. For several months, the spacecraft was transmitting garbled data, and the team struggled to diagnose the problem across a communication gap of 22 light hours. Think about that for a moment. You send a command to the spacecraft. 22 hours later, you receive the result. If the command was wrong, or the result was unexpected, you wait another 22 hours before you can try something else. Diagnosing and fixing a problem on a spacecraft at the edge of the solar system with this communication delay is an exercise in patience and precision that few challenges in engineering can match. The team traced the problem to a chip in the flight data system, a single chip corrupted after nearly 50 years of operation in the radiation environment of interstellar space was injecting errors into the data stream. The solution required sending a new software patch that rerouted the data around the damaged chip, but the patch had to be written to fit in the spacecraft's extremely limited memory, using a programming architecture that dates from the early 1970s, by engineers working from documentation of a system designed before most of them were born. They did it. In April 2024, Voyager 1 resumed transmitting clean, usable scientific data. The team at JPL that works on the Voyager mission today is small. Most of the original engineers who built and launched the spacecraft are gone. Some retired, some deceased. The knowledge of the system has been painstakingly passed down through generations of engineers, maintained in documents and in the memories of the people who have devoted their careers to keeping these two tiny spacecraft alive. They will continue until they cannot. The RTGs will continue to decay. The power will continue to decrease. By the end of the 2020s, there may not be enough power to operate any science instruments. By around 2030, the transmitters themselves may go dark. On that day, whenever it comes, Voyager will stop talking. But it will not stop moving. Both spacecraft will continue on their trajectories through interstellar space for billions of years, long after the Earth has been swallowed by an expanding sun, long after the sun itself has collapsed into a cooling white dwarf, long after everything we have ever known has changed beyond recognition. They will carry their golden records through the dark. Bach and Chuck Berry, and the sound of rain and the sound of a kiss, moving through the void between stars at 17 kilometers per second, carrying something of us out into the forever. Let your jaw relax. Let your hands open. Let your breathing find its slowest, most natural rhythm. You are very close to sleep now. The story is almost finished, but the journey never ends. The greatest discoveries of the Voyager mission are not the ones you might expect. The volcanoes of Io were extraordinary. The ocean beneath Europa's ice may one day prove to be one of the most important discoveries in human history. The rings of Saturn in their full complexity, the geysers of Triton, the alien chemistry of Titan, all of these are profound additions to our understanding of the solar system. But the most important thing Voyager taught us is not about the planets. It is about the enterprise of exploration itself. Voyager was conceived, designed, built, and launched by human beings working with the technology of the 1970s. They did not have personal computers. They did not have the internet. The calculations that determined the Grand Tour trajectory were done by hand and on mainframe computers the size of rooms. The spacecraft were assembled by people with soldering irons and oscilloscopes and the kind of meticulous, painstaking craft that is required when there is no margin for error. And those people got it right. Not just right, extraordinarily, remarkably, almost unbelievably right. The spacecraft they built are still operating. The trajectories they calculated are exactly where the spacecraft are. The instruments they designed are still returning data after nearly 5 decades in an environment more hostile than anything that has ever been tested on Earth. They got it right because they cared, because they understood what they were doing and why it mattered, because the desire to know, the deep, aching, fundamentally human desire to see over the next hill, to understand what is out there, to reach further than any generation before, drove them to a standard of excellence that transcended the ordinary. That desire is not exclusive to scientists or engineers. It is in you, too. It is why you are here, listening to a story about 2 spacecraft launched when your parents or grandparents were young, still moving through interstellar space right now as you lie in the dark. The desire to know what is out there is the oldest human impulse, older than agriculture, older than writing. It drove our ancestors across ice sheets and oceans in boats made of wood and animal skin. It drove us to climb mountains and dive into the depths of the sea. It drove us to look up at the stars and ask what they were and how far they were and whether we were alone. It drove us to build Voyager. And Voyager, in return, gave us the pale blue dot, the perspective from the outside, the view of ourselves as we truly are. Small, improbable, extraordinary, alone on a fragile world in a vast and largely indifferent cosmos. That perspective is not comfortable. but it is honest. And it carries within it something that looks, if you tilt your head the right way, very much like hope. Because if we, this small, young, frequently confused species on this small, young planet, if we were capable of building Voyager, of conceiving of the grand tour, of catching the 175-year window, of sending something to the edge of the solar system and beyond, then what else might we be capable of? What might we do with another century, another 1,000 years? What might our descendants send into the dark? We don't know. We cannot know. But somewhere, right now, the answer is already on its way. 17 kilometers per second, into the void, carrying the sound of rain and the sound of a kiss and Bach. Let your thoughts become soft now. Let the images dissolve. The spacecraft are out there. They will always be out there. They don't need your attention to continue their journey, and you don't need to do anything else tonight. Just breathe. Just rest. Just be here, in the dark, on the pale blue dot, for a little while longer. And now, we come back. From the edge of the solar system, from the cold silence of interstellar space, from the boundary where the sun's warmth finally gives out and the true dark of the galaxy begins. We come back through the heliosphere, back through the realm of the outer planets, past Neptune with its dark storms and captured moon, past Uranus tilted on its strange axis, past Saturn with its impossible, beautiful rings, past Jupiter with its red eye still watching, past the asteroid belt and Mars and Venus and the moon, pale and ancient and patient, back to Earth. This blue, improbable world. From space, it glows. Not metaphorically, literally. It glows with the reflected light of a star it orbits at exactly the right distance to keep water liquid on its surface. It glows with the blue of deep oceans covering more than 70% of its surface. It glows with the white of clouds, perpetually forming and dissolving in an atmosphere that has been slowly, patiently, biologically transformed over billions of years from something toxic to something breathable. And somewhere on that glowing world, right now, you are lying in the dark. You are breathing slowly. Your body is warm and heavy and held completely by the surface beneath you. The thoughts, if there are any, are becoming less like thoughts and more like impressions, half-formed images, the slow dissolving of wakefulness into something else. You are on the edge of sleep. The edge is gentle, there is no drop. There is only the soft transition from one state to another, from the world of thoughts and plans and memories and worries to the other place, the place below all of that, where the body rests and the mind drifts free and the hours pass like water. The Voyager spacecraft are out there, right now, tonight. In this moment, as you breathe, they are 17 kilometers deeper into interstellar space than they were a second ago. They do not know you exist. They do not know anything. They are machines. Beautiful, extraordinary, still functioning machines, but machines. But we know they exist. And in knowing, in caring, in tracking, in sending commands across 22 light hours and waiting patiently for the response, we are doing something that is worth naming. We are paying attention to the universe, which is enormous and ancient and mostly silent, to ourselves, which are small and brief and astonishingly capable, to the journey which began with a window that opens once every 175 years and has not ended and will not end. Pay attention to your breath now. In, out. In, out. Let the story release you. Let the dark hold you. Let sleep come. Somewhere out there, two golden records are moving through the void, carrying the sound of rain, carrying Bach, carrying laughter, carrying the sound of a kiss into the forever, for whoever might one day find them. A message from the pale blue dot. A message from us, from a species that looked up at the stars and wondered, from a species that caught a window open once every 175 years, from a species that sent something into the dark and did not stop listening. Sleep well, sleep deeply. You are home. When the Voyager transmitters finally go dark, sometime in the early 2030s, if the current power estimates hold, what remains will be silence. Not the temporary silence of a spacecraft in standby mode, or the recoverable silence of a system that has failed but can be reset. Permanent silence. The end of the conversation. And after that silence, two objects will continue moving through interstellar space for a length of time that makes the entire history of human civilization look like a single afternoon. In roughly 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. It will not make close approach. 1.6 light-years is still an enormous distance. But in interstellar terms, it is a near miss. In 296,000 years, Voyager 2 will pass within 4.3 light-years of the star Ross 248, a small red dwarf in the constellation Andromeda. These are not destinations. They are accidents of trajectory. The long, straight lines of the spacecraft's paths intersecting, by coincidence, with the orbital positions of other stars. The spacecraft are not going anywhere in particular. They are simply going. And they will go, and go, and go, long after there is anyone left to track them, or think about them, or remember that they were ever sent. Long after the last human being who knew what a Voyager was has been gone for 1,000 years. Long after the civilization that built them has changed into something unrecognizable. Long after the sun has consumed the inner planets and collapsed and cooled. They will go. They are the most permanent things we have ever made. Not permanent in the sense of indestructible. Interstellar space is not empty, and over billions of years, the micrometeorite impacts and cosmic ray bombardment will slowly degrade the spacecraft. Eventually, in some unimaginably distant future, they will be unrecognizable as human artifacts. But the golden records will survive longer. The gold electroplating will protect the aluminium substrate against the erosion of space. The records themselves encode information in a form that does not depend on any particular technology to read. The cover includes instructions in the language of science and mathematics for how to play them. In roughly 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. It will not make close approach. 1.6 light-years is still an enormous distance. But in interstellar terms, it is a near miss. In 296,000 years, Voyager 2 will pass within 4.3 light-years of the star Ross 248, a small red dwarf in the constellation Andromeda. These are not destinations. They are accidents of trajectory. The long, straight lines of the spacecraft's paths intersecting, by coincidence, with the orbital positions of other stars. The spacecraft are not going anywhere in particular. Sleep, sleep.